So what we've been doing for the last few weeks is graphing these things called relations. And I want to start with the definition. We define a relation to be any set of ordered pairs. So, like many of the definitions that I've asked, this is one that I really want you to know and memorize. A relation is any set of ordered pairs. So what could this look like? Well, when I say a set of ordered pairs, what I really mean is a collection, a grouping of ordered pairs. Sometimes those ordered pairs come up to be curves, like this on a graph. Sometimes they're lines. Sometimes they're individual points. But it's any of them. And ordered pairs are these things that we've seen before. They look like x comma y points. So if I wanted to do an example of a relation, I could graph, or I could put these points down: 1, 3, 2, 7, and 3, 8. That's a relation. It's a relation where I have, if I kind of put a t-chart here, my x is 1 goes with a y of 3. And there's meaning behind that. This x equals 1 means that I have a y of 3. Those two are linked. And that linkage is part of why we call it a relation. There's meaning connected between the two of those. We also have 2 linked with 7 and 3 linked with 8. Another way to show this is that 1 is transformed into 3. 2 is transformed into 7, and 3 is transformed into 8. And this right here is called a transformation. That word is actually used a lot in math. Transformation. So we have a name to actually mean all the left ones, all of the x's. And this is kind of a key one right here. Some of you may remember this from last year. Our definition of domain. A domain is all possible, and that's really key there, all possible first coordinates. And since it's all possible first coordinates, my domain for this one right up here would have been the numbers 1, 2, and 3, put in set notation to kind of separate those aside. So let me give you 2 examples of domains here. Here's the first one. If I gave you the line y is equal to 2x plus 7, first of all, you should know that that would graph a line. And second, if I asked you, what is the domain of this? Well, the domain of this really is saying, what are all possible first coordinates? Since I can plug anything into x, my domain would be all real numbers. And we're going to write that and express that as all real numbers. So it could be anything. I could actually plug in anything, and you should say to yourself, that makes sense, because I could take any number, multiply it by 2, and then add 7. There is no number I could not do that to. No number that's on the real number line. And that's what we're talking about. So what about operations that I can't do to any number? Well, here's one. Y is equal to 1 over x minus 7. Its domain would be any real number, except the one number that if I were to plug into this denominator would make that denominator 0, because the cardinal rule in math is you cannot divide by 0. That number that I would plug in would have to be 1. So any real number except 1. And I have a way to write that in set notation. I write it as all x such that x is not equal to 1. And that tells me that this is any real number but 1. So the domain up here was any real number, but the domain right here was any real number except for 1. Just like we have domain, we have a notation for all the possible second coordinates. And that is not called domain, that is called range. Actually, in college, they call that several other things, including target and codomain. But we're going to call it range to be consistent with your books. A range is the set of all possible second coordinates. And so if I go back up to the top here, let's scroll back up, and I just kind of put a little R for range. My range here would be the numbers 3, 7, and 8, because those were all the possible second coordinates. Again, kind of carrying the highlight, that's my range, and this is my domain. And here's another one, domain right here, range right here. So let me go back down. Let's do another example of domain and range. Let's take this one. Let's take this set of ordered pairs 5, 1, 0, -7, 0, 1, and 15, 4. So taking all of those, if I'm going to say what is the domain, I need to list off all the first coordinates. So listing off all the first coordinates would be 5, 0, and 15. You don't want to repeat them, and there's no need to, so don't list the 0 twice. They don't need to be in order, but I just don't want to put the 0 twice. My range now would be the second ones, 1, -7, I already listed 1, and 4. So it's just a listing. They don't really tell you how they're grouped, it just tells you what they are. And again, if I were to highlight, here's my domain, again in yellow, and here's my range again in green. Highlight it all there, and then right here too. So that's domain and range. Now, we're going to kind of move ahead to something else that you probably have talked about before, and that's a function. This definition is one that I do want you to memorize, and I will ask this multiple times. So, we're going to start. A function is a type of relation. So there's many types of relation, but a function is a special type of relation in which each element of the domain, meaning each part of the domain, so every number that could be a part of the domain, but each element of the domain is, we'll use the word transformed into, one and only one element of the range. A rather lengthy definition, and one you're going to have to practice. And I would start ASAP, because I'm probably going to ask this on a pop quiz either tomorrow or the next day. I'm known to do that. So a function is a type of relation in which each element of the domain is transformed into one and only one element of the range. What that means in kind of talk is each x becomes only one y. Meaning if I'm an x, I need to know what I'm going to become. So it can ask the question, what does x become? If you can answer that for every possible x, then you probably have a function. Let me show you kind of how these functions work and what they can look like. So here's another example of one. We're going to call this function function f. That's just going to be for right now. And function f is going to take x and it's going to transform it into 7x minus 2. And what I mean by that is f is the rule that changes x into 7 times x and then subtract 2. So I could tell you this is for any real number, but let's limit the domain. Let's say my domain is going to be just 3 numbers, -3, -50, and -2. Okay, if I said my domain is 3 numbers, can you tell me what the range would be? It would also be 3 numbers because each x becomes one and only one y. And I would find that by saying, let's see what negative 3 becomes, let's see what negative 50 becomes, and let's see what negative 2 becomes. And since the rule is to take this x value, multiply it by 7, and then subtract 2, well, I'm just going to do that to all three of these. 7 times negative 3 minus 2, 7 times negative 50 minus 2, and 7 times negative 2 minus 2. And we'll just evaluate those out. That would be negative 21 minus 2, which would be negative 23. This would be negative 350 minus 2, or negative 352. And this would be negative 14 minus 2, or negative 16. So I'm just going to list those over here. I'm going to put them right below their respective x values, even though I don't have to for range. I'm just choosing to. And that answers it. Let's try another one. Let's do a different function. Let's go g. G is the function that takes y, and it transforms it into y squared plus another y. So if I say my domain is 0, negative 3, 3, and 2, well, can you tell me what the range would be? Okay, so off here I'm going to do the work. I'm going to go 0 squared plus 0, and that would be 0. Then let's go negative 3 squared plus a negative 3. Notice how I put the negative 3 in parentheses to be really careful. That one I might have to do a little work here. Negative 3 squared is 9. 9 minus 3 is 6. Then we're going to do 3 squared plus 3, which is 9 plus 3, or 12. And finally, 2 squared plus 2, which is 4 plus 2, or 6. Oh, but you see I already listed 6, so we're not going to list 6 again. And I'm just going to leave it like this. And you may be like, well, wait a minute, you just lost some information. Well, yeah, I did. Domain and range don't tell me what the ordered pairs are. They just tell me what the possible x's and what the possible y's are. One way to show ordered pairs in a different way would actually be to do with a different kind of diagram. If I were to list the domain of 0, negative 3, 3, and 2, and then I list 0, 6, and 12, this is a fun one because this is an arrow diagram. I'm going to say 0 becomes 0, and negative 3 becomes 6, and 3 becomes 6. Kidding. 3 became 12. 2 became 6. Okay, oops, that one works. And that's a function because if I'm x, I know what y I become. There's no question as to what y that you would become. So, let's go back to some other types of examples. It is very possible for you to have function notation where you've got an f of x equal to one thing and a g of x equal to another. Notice how I said that. This is called f of x. Sorry, pause there. Like I said, we call that f of x. This does not mean f times x. This f of x notation is basically like y. And some of you may be like, well, what the heck was wrong with y? Why didn't we just put y equals? Well, there's a very good reason for this, and we're going to show it to you. First of all, when we use the f of x like this, it means it's solved for y. It shows that it's a function, and that's kind of very valuable. This is actually showing that we have two functions. And that's very good. We have two functions because it's in function notation. And that's what this is called. This is called function notation. So I've got two functions. I've got an f and I've got a g. And I'm going to show you some of the things we can do with that. Let's look at this one here. I'm going to say, what is f of negative 14? So not f of x, f of negative 14. Well, that means to take negative 14 and substitute it in for x. It's really easy to do, you just have to know what that means. So f of negative 14 is to say 4 times negative 14 and then plus 2. 4 times negative 14 is negative 28, and that would be negative 26. So f of 14 equals negative 26. And that's what we have. By the way, or BT dubs, that means that we had an ordered pair of negative 14 and negative 26, because that's like an xy ordered pair. And I do want you to know that. Okay, letter B. G of negative 4. Okay, g was a different function. G was this one here, the x squared minus 2x. So I'm going to substitute. We're going to do negative 4 squared minus 2 times negative 4. It's just a simple substitution. Negative 4 squared is 16. Negative 2 times negative 4 is positive 8. And that gives me 24. So g of negative 4 is 24. And I'll circle that and move on. Let's switch colors to a little bit more of a darker one. Let's do g of 1/5. G of 1/5, same thing with the g. It means to take the number, square it, and then subtract 2 times that, because that's what we defined it as. We said, okay, that's x squared minus 2x. So 1/5 squared is 1/25 minus 2/5. 1/25 minus 2/5. Well, if I change the 2/5 into 10/5, I have 1/25 minus 10/5, or sorry, 1/25 minus 10/25. 1 minus 10 is negative 9, so that's negative 9/25. Let's do another example. I'm going to sort of grid these out here. F of 3/4. Okay, so we're back to the F1, which was 4 times a number, and then plus 2. Well, 4 times 3/4 is 3, and 3 plus 2 is 5. So f of 3/4 is 5. I forgot to circle the previous one too, so let's write that down. Oops. Okay, that's good enough. Let's do another one. 1/3 g of negative 2. Okay, let's pause here. 1/3 times g of negative 2 is really what that means. So I'm going to stick the invisible dot in here. I'm going to keep the 1/3 on the outside, but then I'm going to do g of negative 2 separately, which is negative 2 squared, and then minus 2 times negative 2. So then that's 1/3 times 4 plus 4, or 1/3 times 8, or 8/3. So 1/3 g of negative 2 is 8/3. Last example of this one, I'm going to do 2f of a minus 3. This is a little different. I've got a minus 3, but I'm still going to do the same thing. I'm going to make this a 2 times, put some parentheses down, and then f of a minus 3 means to do 4 times a minus 3, but then add 2. Well, 4 times a minus 3 is 4a minus 12 plus 2, and then that's 4a minus 10, and now I'm going to distribute the 2 to get 8a minus 20, and that's simplified. I'm just going to circle that right there. So, in general, we know that, and this is kind of a little review thing here, we've learned that the domain is all possible x's. We've learned that the range is all possible y's. We know that a relation is any set of ordered pairs. And we know that a function, well, functions themselves have a little trick. You need to know the definition of a function. You need to remember that. I'm going to expand on this function thing for just a bit. I'm going to do 2 examples. 1, 2, 3, 4, 5. And this is going to be 1, 2, 3, 4, 5. And on the left one, we're going to draw an arrow from 1 to 4, 2 to 4, and 3 to 5. And on the right one, I'm going to go 1 to 4, 1 to 5, 2 to 4, and 3 to 5. One of these is not a function, and I'll show you why. This one is a function. because if I'm x, I know what y I go to. That's the x and that's the y. This is the x and this is the y. It's a function because each x goes to one y. Even though there's repeat on which y it goes to, each x goes to one y. This one on the right is not a function. And that's because the number 1 went to two y's. Right here. This 1 either went to 4 or it went to 5, and I don't know which one it goes to. So it's not a function. Oops. We're going to continue this one next week, so stay tuned.